Okay, well, we thank you everyone for coming. We're very pleased today to have Yuval Filmus speaking on some analysis of Boolean functions type work. If you happen to be have a webcam available, we welcome you to turn that on. Of course, no pressure. Um, Otherwise, I'll leave you to it, Yuval. Thanks again.
Okay, so thanks for the invitation. So I'm going to talk about joint work with Irit Dinu from the Weizmann Institute and Prahlad Harsha from the Tata Institute for Fundamental Research in Mumbai, India. Okay, so today we're going to discuss, well, not quite Boolean functions, but functions on the Boolean cube. So can you see my pointer?
Yes,
Yeah,
it's good.
yeah. So our functions are going to get as input n bits. A bit is either 0 or 1, and they're going to spit out some real number, okay? And we really think of them as polynomials, okay? So functions on the Boolean cube on 0, 1 to the n, you can really think of them as the same thing as multilinear polynomials. Okay, and more than that, every function on 0, 1 to the n has a unique representation as a multilinear polynomial. And the degree of this polynomial is the same as the degree of the function, okay? So we say that the function has degree d. This is going to be important in this talk. This is why I'm stressing this. If it can be written as a degree d polynomial, or equivalently, if its unique representation as a multilinear polynomial has degree d. Okay, and we will say that the function is Boolean if whenever you put in 0, 1 inputs, then you also get back a 0, 1 output. Okay, so in this field of analysis of Boolean function, we often study Boolean functions on the Boolean cube. But also quite often we study functions which are real valued on the Boolean cube. And this is what we're going to do here. Okay, and the question we are going to tackle is not this question, not which degree D functions are Boolean, but let's start with this question. So which degree D functions are Boolean? So it's not very hard to answer this question for when D is equal to 1. So maybe I should have paused and asked, okay, so which Boolean degree 1 functions can you think of? Okay, but that's too late now. So there are the constant functions and the so-called dictators, xi and 1 minus xi. Okay, so this is an explicit list. We also have such an explicit list for degree 2 functions, but in general, we can say, following Nissan and Szegedy, that functions of degree d, Boolean functions of degree d, are what are known as juntas. Okay, so this is a terminology from social choice theory. A junta is a function which depends on a constant number of coordinates. And in this case, the constant is going to depend on d. Okay, so I'm just mentioning this because the title of my talk is Sparse Juntas, where juntas was in quotation marks. So this is the same meaning of junta as in the title of my talk. Okay, people familiar with the literature will recall that Nissan and Szegedy gave a different bound, but well, we won't care about such details here. Okay, so this question is not very interesting because Boolean degree D functions are not so exciting. They depend on a constant number of coordinates. Okay, that's the main point here. It gets more interesting when we answer the following question. So which degree functions are close to being Boolean? Okay, or sometimes we think of it in the opposite way. Which Boolean functions are close to degree D? Okay, these are really the same question. Okay, so this is what we're going to answer today. This is how these sparse quantas are going to arise. But first, let's make this question more precise. Okay, so here's an example answering this question in the case d equals 1. Okay, this is in this area quite famous theorem of Friedgut-Kalai and Naol. Okay, so suppose that f is a real valued function on the Boolean cube and it happens to be degree 1. And it is close to Boolean in the following sense. So if you take a random x, we'll soon say what the distribution is, and compute its square distance from 0, 1. So in this area, we always look at L2 measures. Then this square distance to 0, 1 is on average small. It's at most epsilon. Okay, so one way to obtain such a function is to start with the Boolean degree 1 function and to just switch around a few of the values, add a bit of noise. And what the theorem says is that this is really the only way of obtaining such a function. Okay, so and you have to add this noise so that the function remains degree 1. This might be a bit difficult. So if you have a function f like this, which is degree 1 and it's close to being Boolean in this sense, then the only explanation is that there is a genuine Boolean degree 1 function, g, to which f is close. Okay, and how close? Order epsilon, and you can, if you want, you can even get a better bound, but this will be good enough for us. Okay, so this is a Friedel-Calaino theorem, and we'll state it in a more succinct form soon. But let me just say that this result, it assumes implicitly the uniform measure in X. Okay, so X is chosen uniformly at random from all 2 to the n different points in the Boolean cube. This measure, which will show up later on, is denoted mu half. Okay, and I will explain why in a bit. Okay, so this is the case d equals 1, and we'll soon see what is the general case for general d. Okay, so this is again the Friedel-Calaino theorem, and I'm putting it here because I want to write it in this way, which is a bit more succinct. So suppose that f is a degree 1 function on the Boolean cube, which is epsilon close to Boolean. Okay, epsilon close to Boolean means this thing, with respect to mu half. So this is the distribution of x. Then f is order epsilon close, okay, this thing, with respect to the same measure, so I won't repeat it, to some Boolean degree 1 function. Okay, so the only way to be an almost Boolean degree 1 function is if you're almost a Boolean degree 1 function. This is one way to think about it, like where do you put the parentheses? It doesn't matter, it's the same thing. Okay, so this was the case d equals 1, and I hope I went over it slowly enough so that you can actually get something. And now let's move to the degree d case. Okay, so maybe you have a guess to what is a degree d case. So suppose that f is a degree d function, which is epsilon close to Boolean. What should f be order epsilon close to? Maybe some crowd participation, don't be shy. Okay, so the crowd is a bit slow today. So you would expect that if f is a degree d function, let's say a degree 10 function, which is epsilon close to Boolean, then it's order epsilon close to some Boolean degree 10 function. And this was indeed proved by Kindler and Safra in 2004. It is exactly what I just said. And here it's nice to say something about this result. So it's never been published. You can find 2 different drafts of this paper on Guy Kindler's website and on Muli Safra's website. They're not quite the same, although they're very similar. One of them contains some notes, like maybe we should change this, maybe we should do that. But you can find a version in Guy Kindler's PhD thesis, which is what I usually cite. And also by now there's another published proof of Keller and Klein. So if you are worried that nobody has actually gone through this proof and verified that it's correct, then you should be, I guess, less worried now. Okay, so these are 2 results. These results, they come up like they're being used in experimental combinatorics. So sometimes we're exactly in the situation here that we have a Boolean function which is close to degree d, and we want to conclude that the function is essentially a junta, and we use the Kindler-Safra theorem. Yeah, this is how I got to know this result. So it's actually useful for something, for some notion of useful. Okay, so this was some classical stuff, and now for some more modern stuff. So far we've seen theorems which were about the uniform distribution over the Boolean cube, which is quite natural, and it's often the case. We are often interested in the uniform distribution over the Boolean cube, but not always. Sometimes we're interested in the bias measures mu p. Okay, so what's the mu p measure? So still, it's some kind of measure on the Boolean cube, but now the marginals are p biased. So the probability to get 1 is p rather than 1/2. Okay. Why would we be interested in this? So if you ever heard about random graph theory, then you probably heard about the Erdős-Renyi GNP model. So this is the same thing. Okay, in the GNP model, every edge is inside with probability p. Okay, so this is maybe where this thing originally came into this area. Okay, so if you've maybe heard of a result like the sharp threshold theorem of, I guess there are several versions, then these all concern this p biased setting. Okay. It also comes up in other places, for example, in theoretical computer science, in an area known as hardness of approximation, and also in extremal combinatorics. So again, this is something which is actually useful. So what happens to these theorems we've seen above? So both of them, they hold for any constant p, like maybe not if you take the original proof, but you can still show that they hold for any constant p. Now, this means that there's some big O's in the statements, and they degrade with p. As p gets closer to 0 or to 1, then this constant blows up, and for some constant p, the theorems become just false, as we're going to see in a moment. So now I can tell you what we're going to do really in this talk today. We're going to describe what happens when p is small. Okay, so now we think of p as completely arbitrary. It could depend on n, whatever. And we will assume that p is at most a half, just to make the statements a bit more concise. This is not really a big deal because you can always flip zeros and ones if you're worried about it. Okay? So that's the goal for today. And let's start with the FKN theorem for small p. So if you recall, the FKN theorem was the case d equals 1 in the previous question. Okay, so here we're given a Boolean degree 1 function, and it's epsilon close to Boolean with respect to mu p for some p. Okay, so p is at most a half, but otherwise we can think of it as small. So if p is constant, then we know that f is order epsilon close to either a constant function or to a dictator, to a function depending only on a single coordinate. But this is no longer the case. Well, we'll see in a moment, but this is no longer the case when p is small. So when p is small, then f is really close to either a sum of several coordinates or to 1 minus a sum of several coordinates. Okay, and how many coordinates? So roughly square root epsilon over p. Okay, so you can see that you can recover the original formulation, like the p equals half case from this result, because if you fix p, then for small enough epsilon, the maximum is going to be 1. And if epsilon is not small, then, well, the theorem is trivial anyway. Okay, and we'll see in a moment where this strange bound square root epsilon over p comes from. Okay, and let me stress here that the big O constants that you see on the slide are independent of p. Otherwise, it would be pointless because we already know that this result holds for constant p. Okay, so this is not the topic of this talk. The topic of this talk is a degree t case, but we'll start with this baby case. Okay, so here is again the theorem in a more succinct way, and now let me explain to you where this strange bound squared epsilon over p comes from. Okay, so why this strange bound on n? So the idea is, let's say that f was indeed epsilon close to this sum, xi1 plus 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 xin. I didn't say, but these coordinates have to be distinct, like different. So suppose this was the case. Let's see what this function f behaves like. Okay. So roughly speaking, I mean, it's not really true, but roughly speaking, the distribution is close to Poisson with expectation NP. Okay, you can say that this really depends on the relation between n and p, but let's not worry about it. And this means now you can do a calculation that the probability that this function is not Boolean is something like np squared. Okay, and we want this thing to be epsilon. We actually want something stronger. We want the sum to be epsilon close to Boolean, which is a stronger statement, but let's not worry about the difference. This would be fine. So if we just look at this bound, okay, so we want this number to be something like epsilon. Okay, and indeed, if you plug in this value, square root epsilon over p, you multiply it by p and you square it, then you get epsilon. Okay, so this is where this bound on n comes from. And the upshot is that these functions are actually close to Boolean. Okay, and what does this mean? This means that this theorem is essentially tight up to the constants, because I told you, you give me any degree 1 function, which is epsilon close to Boolean, then it must be close to one of these functions. And indeed, all of these functions are also close to being Boolean. So up to some constant factors, this is like an if and only if statement. Okay, so I find this kind of thing pretty cool. Unfortunately, I think up to now, I'm not aware of any kind of good applications of this result, but maybe some of you will find some. Okay, personally, I care less about applications and more about the theory, but I think it's also good to care about applications because otherwise you might end up proving the wrong theorems. Okay, so this was the case of degree 1. And now let's see what happens in degree D. Okay, so this is the work that I'm actually going to talk about in this talk. And this is the main focus. Okay, this is the Kindler-Safra theorem for small p, or the biased Kindler-Safra theorem. So here's the statement. So suppose that f is a degree D function, which is epsilon close to Boolean, with respect to some mu p. Then f is order epsilon close to some degree D function g, satisfying some properties that I will list on the following slide and then explain them one by one. Okay, so here I'm just trying to explain what kind of result we want. So again, if f is a degree D function which is close to Boolean, then you want to say that it's close to some degree function g which satisfies certain properties. And furthermore, we want all of these functions to be actually close to Boolean. Okay, this is exactly what we had in the degree 1 case. Yeah, so here we gave an explicit list of functions. So in the degree 1 case, f must be close to either sum or its negation. And this is tight in the sense that these sums are actually close to Boolean. Okay, so our goal here is to find a similar type of statement. But it's not so clear whether we're going to have an explicit list like we had in the case d equals 1. So in the original version of the paper, we gave some examples of some degree 2 functions which could be close to Boolean. And yeah, it's not so clear how to find the general structure. And indeed, we described some properties of G, but we didn't have like an if and only if characterization. But eventually we got such a characterization. And this is what I'm going to explain to you today. Okay, so unfortunately, the characterization is, I wouldn't say complicated, like I've seen more complicated theorems in my lifetime, but it's less explicit for sure than what we saw before. Okay? So let's say that f is a degree D function, which is epsilon close to Boolean with respect to some up. Then f is going to be order epsilon close to a degree D function g, which satisfies the following three properties, which I'm going to go over one by one. Okay, so first, this you can understand on your own. G is Boolean on inputs which have small Hamming weight. Okay, and we'll see what this implies in a moment. Second thing is that G has few minimal non-Boolean inputs of every weight. Okay, we don't yet know what this means, but we'll see in a moment. And three, G is sparse. Okay, we also don't know what it means, and actually in the paper we use a different term, but this is a term which is more fitting and used by experts in related areas in combinatorics. Okay, and furthermore, any degree D function which satisfies these three properties is going to be order epsilon close to Boolean. So in this sense, the theorem is tight. Okay, so maybe this is not the theorem we want, although as we'll see in a few slides, and we can actually get some, what I think are somewhat interesting corollaries, even just from this formulation. But in a sense, this is really the best that you can, because this list of functions, well, it's tight. Okay,
Yuval,
so
if I could
what?
ask
Yeah.
a stupid question. So we
Yeah.
already know f is epsilon close to Boolean. That by triangle inequality implies the last line of this theorem.
No, no, no. So this function g here is any function divorced from the function f, is any degree D function which satisfies these three properties. Okay, so it's not
Right.
supposed to be obvious that it's close to Boolean.
I see. But it's close to f, and f is close to Boolean.
Well, but no, the claim here is a bit more general, that you give me any degree D function g, which satisfies these three properties. Okay, in this picture, there's no f. And for any such function g, you can find this function f.
Got it. Okay, I'll think
Or
about it.
rather,
Thank you.
so this function g itself, you can think of it as playing the part of the function f. Okay, yeah, so like it's a good question. So both parts of this theorem
Sorry,
were, yeah.
can I ask for a further clarification on this question? The conclusion is not exactly what you would want because you don't know whether the last Boolean function is actually degree D. Is that
No,
the
no.
only thing that's missing?
So well, it depends. So the conclusion is what I want. So what I wanted is I wanted to find an explicit set of functions for some definition of explicit, such that any such function f satisfying this is close to one function from this list, and moreover, all the functions from this list are themselves close to Boolean.
I see.
Okay, so this is what I wanted. But I mean, you can take another set of functions. You can just take all the functions which are degree D and epsilon close to Boolean. So this is another explicit set of functions. So the point here that in the degree 1 case, this explicit list of functions was even more explicit. I just gave you all the functions, you know. But here, this is too much to expect because there are many possibilities. But in a sense, this is the best we could do. But this is enough to prove some corollaries, which maybe shows that these properties are useful.
I see. And is there any possibility that for some weird such function, the Boolean functions that are epsilon close to it are not degree D? Or you can guarantee that you can also find degree D Boolean functions close to it?
Well, I can guarantee that I can find some degree D function which satisfies these properties and is close to f. Of course, you can find other functions, like the closest Boolean function to f is you just take f and you round it. Okay, so this would be even closer, but probably not degree D.
Okay, I see. Thank you.
Yeah. So this is the game here. We want some kind of approximation which will be useful for us. And this will turn out to be useful in some corollary I'm going to explain later. Yeah, any more questions? You should ask questions because otherwise the talk is too short. So, but you can keep them from later. Okay, so now we go over these three conditions. Okay, so again, what we're trying to do here is we have a degree D function which is close to Boolean, and we're trying to understand what it looks like. Okay, so I'm going to give you some kind of explicit list of functions which this function f must be close to. Okay, and these functions are all degree D functions which satisfies these three properties listed here. And now we're going to go over all of these properties and explain what they mean. And then maybe you'll see, maybe you'll get to decide whether this is explicit enough for you or not. Okay, so the first condition that this approximating function g is going to satisfy is that it's Boolean on all inputs of low Hamming weight. Okay. Now, what does this mean? So we can expand G as a multilinear polynomial. Yeah, this is what's written here. Maybe this expression is kind of complicated, but anyway. And I should stress for those of you that know anything about Boolean function analysis, this is not the Fourier expansion. This is some other expansion. And then what this condition really means is that these coefficients CS, they are what we call quantized. Okay, so they cannot be arbitrary, but rather each of them belongs to some finite set of possibilities. Okay, so in this sense, this recalls what we had in the degree 1 case, where these coefficients were either if the constant term was 0, then all the coefficients were 0 or 1, and if the constant term was 1, then all the coefficients were 0 or -1. Yeah, so this is the example here. So when d is equal to 1, then if you substitute x is equal to 0, then you get that the coefficient of the empty monomial, the monomial 1, or the constant coefficient of g must be either 0 or 1. Okay, this is true for any d. And now, without loss of generality, let's consider the case where this coefficient is 0. Then, if you substitute a vector of Hamming weight 1, so EI is the ith unit vector, then you get that the corresponding coefficient is either 0 or 1. And this corresponds to the structure given here. So I'm sorry, this should have been an X. Okay, so I'm not sure if you followed, but this condition is essentially the same as saying in the degree 1 case that G is either a sum of things or 1 minus a sum of things. Okay, so this is what you get in degree 1 for d equals 1. For d equals 2, then the condition is more complicated. Then we have more possibilities, but we still get something of a similar sort. So these coefficients of this polynomial in this expansion, they're not arbitrary. They come from only a few possibilities. And really, these coefficients, if you go over all Boolean degree D functions and you look at all the coefficients that can happen, then these are also the coefficients that can happen in this approximation function G. So this is also what happens here. Okay, so this was the first property that this function G satisfies. Now the second property is going to allow us to bound n. Yes, in the degree 1 case, then we said that G is either of this form or 1 minus this form, and also we had a bound on n. So this bound on n is going to come from the second condition. Okay, so here's the second condition. So G has few minimal non-Boolean inputs of weight E. So now I can explain what this means. So X is a minimal non-Boolean input. If when you plug in X to G, then you don't get something Boolean. But if you take anything smaller, so if you change ones to zeros, then you always get something Boolean. Okay, and maybe I'll give an example. So again, in the case d equals 1, if you take this function G, then here's a minimal non-Boolean input. Okay, so you just take some vector of Hamming weight exactly 2. So the value of G on this vector is 2, which is not Boolean. But if you look at all the vectors below it, then the value is either 0 or 1. Okay, so this is the minimal non-Boolean input. It's not a complicated concept. And what this condition says in the case d equals 1, so the number of minimal non-Boolean inputs is exactly n choose 2 for this example. Okay, and then either n is at most 1, or if not, then this is like n squared. And since n squared has to be order epsilon over p squared, then you conclude that n is order squared epsilon over p. Okay, so this kind of this condition, it translates to a bound on n in the case d equals 1. For larger d, then it's a more complicated condition. Now you can ask, this is not one condition because here there's a parameter e which determines the weight. So maybe these are infinitely many conditions. Yeah, but as it turns out, all the minimal non-Boolean inputs have weight at most order 2 to the d, so this is really only finitely many conditions. Okay, in the paper, if you're very, very interested, you can look at the list of conditions in the case d equals 2. It will be somewhat long, and that's why it's not on the slide, but you can do this explicitly if you really want, at least for d equals 2. Okay, so far, when d is equal to 1, then condition 1 and condition 2 are really enough to specify everything. So if you look at all the functions g that satisfy condition 1 and condition 2 and are also degree 1, then this is exactly the kind of functions promised by the biased FKN theorem. But it turns out that we need one more constraint for general D, and this is this sparsity condition. And this is also where the term sparse junta comes from. Okay, so we again consider the same expansion as before. And now let me first give you a special case of this condition. So it states that on level E, so there are at most 1 over p to the e non-zero CS. So level E, it means all the sets S of size E. Okay. So like there are at most 1 over p many non-zero CIs, and at most 1 over p squared many non-zero CIJs, and so on and so forth. Okay, so the sparsity is a bit stronger condition, but this is maybe most of it. And if you think of it, this also implies the following thing. Okay, so let me take a random input, and let me say that the monomial is active if it's 1. Okay, so I think of this g as a polynomial, and some of the monomials are missing. So if CS is equal to 0, then the corresponding monomial is missing. And I look only at the monomials which are actually there. And for a certain input x, I can ask how many of these monomials are actually evaluated to 1. Okay, and this sparsity condition, this what's written here, you can check that it implies that the expected number of these monomials is order 1. Okay, so on a random input, in a sense, this function looks like a junta. Okay, I'm not sure if you find it convincing, but this is why we call this a sparse junta. This is actually the origin of the name. Okay, so again, if I take a random input distributed according to mu p, and I check this function g is eventually the weighted sum of monomials, then this weighted sum is going to contain an expected number in expectation, it's going to contain a constant number of monomials. Okay, and that's what we think of it sometimes as a sparse junta. Okay, and here's the action condition. So for all sets T, if you look at all the sets S extending T by E elements, and I want at most order 1 over p to the E of them to be non-zero. Okay, this is like looking at the links in the support hypergraph of the function. Let's not worry about it too much, although this is the action condition. This is a kind of a hereditary form of this condition here that is conserved by substitution, but let's not worry about it. This is just some condition that we need. And why do we need it? So technically, it allows us to transition from this kind of statement, that f and g are close in L0, to this kind of statement, that f and g are close in L2. Okay, so, well, there's not too much more I want to say about this. Okay, so here's a recap. Here's the result again. So I won't repeat it because I already I went over the statement a few more times, but this is just here because soon we will see some other versions of this result. Okay, so I haven't described the proof at all. We're going to say a few words about it in a moment. Okay, there's a monotone version of this result, but I think we're going to skip it and maybe we'll come back to it later. But very briefly, if f is monotone, then you can guarantee g to be monotone. Okay, so let's not worry about the details too much. Okay. And now let's see some kind of application of our structure theorem of this Kinosapo theorem for small p, which maybe illustrates that the kind of structure that we prove is actually useful for something. So here's again the case d equal to 1. Yeah, so you already know the statement because it's been on a few slides before. And here is a corollary. Okay, so let's say that f is this degree 1 function, which is epsilon close to Boolean. Then this function is square root epsilon close to some Boolean degree 1 function. And in fact, square root epsilon plus p close to a constant Boolean function, so to 0 or to 1. And because we think of p as small, then maybe this thing is the same as square root epsilon. Okay, so what does this mean? What does this mean? So if you're okay with a structure statement where the error in the approximation is square root epsilon rather than epsilon, then you really get the original result. And then you recover the original statement. So when p is constant, then it's true that if f is degree 1 and epsilon close to Boolean, then it's order epsilon close to a Boolean degree 1 function. When p is small, this is no longer true. You get this more interesting structure here. But it is true if you're willing to lose the power in epsilon. Okay, so you can say in a sense that this question is boring because if you think of p as small compared to epsilon, then really the only functions satisfying this are essentially constant. Okay, this is a more negative way of looking at this corollary. Okay, but this corollary really it follows quite easily from this description. Okay, so there's like an issue of whether you look at it with your naked eye or with a telescope. Like if you look at your function through a telescope, then you find this more interesting structure. But if you just look through your naked eye without any instruments, then you just see a Boolean degree 1 function or even just a constant. Yeah, so I find this quite interesting. Okay, so what happens in the degree d case? And a similar type of statement holds. So there are some exponents, mu d and md, such that if my degree d function is epsilon close to Boolean, then it's order epsilon to the something close to a Boolean degree d function, and order epsilon md, order epsilon to the something plus p close to some constant Boolean function. So either to the 0 function or to the 1 function. And we can even calculate one of these constants, okay, this small md. So it's the inverse of the maximal capital MD such that some degree d polynomial p satisfies its first MD values on the integers are Boolean, and also a non-triviality assumption that p of 0 is different from p of 1. Okay, and we can use our structure theorem to prove this kind of statement, which means that the structure that we find is useful for something. Okay, so as an example, when d is equal to 1, then we saw that this optimal exponent is 1/2. Okay, I didn't say, but these exponents, rather, this value here is optimal, so you cannot get anything better. So in this case, this polynomial is the boring polynomial, which is just the identity. Okay, and you can see that p of 0 is 0, and p of 1 is 1, and p of 0 is different from p1. So this gives us capital M1 equal to 2, and indeed this exponent is 1/2. Okay, for d equals 2, it's more exciting, but this is in the paper if you care to look. Okay, so I just flash this. So using the same sort of Poisson approximation, you can show that if I didn't give you such a polynomial, then you could construct an example showing that you cannot beat 1 over md. So I won't go through the details. And the hard part is to use our structure theorem to show that we can actually prove this bound. Okay, so the two directions is one is that you cannot get anything better than 1 over md, and the other, the more interesting direction is to show that it is possible to get this bound, which is written here. Okay, so here is the theorem once again, and I'm presenting this here because now I'm going to tell you something about the proof. Okay, not too much, but something about the proof. Sometimes the proof is more interesting than the result. I don't know if this is the case here, but still, there's some things which are interesting about the proof. It illustrates some kind of approach to handling small p, which is different from some of the other approaches. Okay, so the basic idea behind the proof is that p is 2p times a half. Okay, so maybe this doesn't sound very deep, that p is 2p times a half. But still, this is really the main point. So this theorem is a statement about functions analyzed with respect to this mu p measure. And here's a strange way of sampling this mu p measure. So we sample a subset S according to mu 2p, which means that we put in each element with probability 2p. And then on the indices outside of S, we just put 0. And on the indices inside S, we just flip a random bit. Okay, so you can check that now the marginal of each coordinate is exactly p. Okay, because in order to survive this stage, it has its probability is 2p, and in order for it to be a 1, then this happens with probability 2p times a half, which is exactly p. Okay, so this is not anything too deep. Okay, so what does it mean? So denote this f restricted to S to be f when I restrict to inputs which are 0 outside of S, sorry. So this kind of sampling according to mu p implies that on average, this restriction is epsilon close to Boolean, where by on average, I mean when we sample S according to mu 2p. Okay, this is really the same thing. So I'm assuming that f is epsilon close to Boolean, and using this kind of two-step approach, then it really implies that these restrictions of f are on average epsilon close to Boolean, where by an average I mean when I sample S according to mu 2p. Okay, and why is this useful? So here's what the proof is going to look like. So I apply the standard Kindle-Safra theorem for each of these restrictions to get a Junta approximation for f restricted by S. Yeah, so the Kindle-Safra theorem for constant p, in this case p is equal to 1/2, it approximates each of these functions by some Boolean degree d function, which is a Junta. Okay, so I get all of these Juntas GS. And then I'm going to paste them together to a single function g using what's known as an agreement theorem. So this is an idea from, I guess, PCP theory. PCP is something in theoretical computer science. Okay, so I'm obviously skipping many details here, but this is really the main approach. After step 2, there's some step 3, which is fixing of g, so that it actually satisfies the properties listed above, but the main idea is this two-step approach. And if you want a better illustration of this two-step approach, then on my website somewhere you can find a proof of the d equals 1 case using this approach, which is a lot shorter than the general case. I can use this opportunity to mention some other approaches. So in particular, there is invariant function analysis. There's some tool known as hyperconductivity, which is usually what you need to prove theorems. And this hyperconductivity, it doesn't hold for small p, but there's another version which does hold, known as global hyperconductivity. Okay, so this approach was pioneered by Noam Lifshitz, now at the Hebrew University, and this is the other main approach for dealing with small p, and it's quite fruitful. So you can see he has dozens of papers that use this approach. And it also applies to other domains. Okay, so let me just close by very briefly mentioning that this same sort of approaches are described in this talk can also be used to prove results on other domains, for example, on the symmetric group. Okay, so on the symmetric group, you can think of the input permutation as represented by these indicators xij. So these are Boolean variables that indicate whether the permutation maps I to j. Okay, and the function is just degree 1 if it can be written as a linear combination of these xij's. And then you can ask, okay, so which degree 1 functions are Boolean? So we have some list. And then you can ask which degree 1 functions are close to Boolean. Then the answer is what you see here, which resembles what we've seen above for the Boolean cube. So it's the same kind of answer, and also it's a similar kind of proof. And we have a similar kind of corollary. Okay, so these functions are close to Boolean degree 1 functions. So this is again a corollary of the same kind of structure theorem. Okay, and yeah. So the proof, I'm just going to flash it. It's very similar. We find another way to sample a random permutation, which allows us to reduce to the case of the unbiased Boolean cube. So I won't go over the details, but they're in the slides, which will be posted, so you can look them up, and also in my paper. And I just want to close by mentioning, if you're interested in this sort of thing, that the degree D case of this result is still open. Okay, so we know what Boolean degree D functions look like even on a symmetric group, but we don't know what degree D functions which are just close to Boolean look like. I mean, we know what the result should be, and we know it should be possible to prove it using the same approach, but there are some issues. So if any of you is interested, then come talk to me in an online sense. Okay, so this is more or less all I had to say, except the things that I didn't say. So thank you, and I can take more questions now.
Thanks so much, Yuval. There was a question in the chat asking for a link to the paper.
Right. So yeah, let me see what the paper is called. We have a few different versions, that's why I can't remember, but you can find it on my homepage. So if you just Google Yuval Filmus, you'll find my homepage. And there you'll find a list of publications. Okay, so as is common for many of us, there are quite a few, but you can navigate to Boolean function analysis. And then the first one is Sparse Juntas on the biased hypercube. Okay, so you can find it there, and it's also on archive, and also on something known as ECCC, which is something in TCS. And there you can also find this paper in the symmetric group, which I spent a few minutes discussing. Right. So you can see that the original version was in 2017 and still not published. Yes, it happens. Yeah, let's move to a more informative slide.
Would you be able to say a couple sentences about this agreement theorem?
Yeah, so we have these GSs, and we think of them as colorings of the D tuples of subset of S, or rather of all subsets of S of size at most D. Now, if you look at two different S's which have a large intersection, then you might expect the coefficients which are in common to agree. And why would you expect this? So, because both are approximating eventually the same function. Okay, so indeed you can prove using this sort of argument. You also need to use that these juntas are form an error correcting code, but using this sort of argument, You can show that in some appropriate sense, these different GSs, they need to agree in the sense that their coefficients agree. And then you want to say, the only way in which I can have this ensemble of GSs which agree is if I have some global G, such as these GSs, they really come from this global G by restriction, on average. And this is what this agreement theorem gives you. Okay, so in the original version, we had a complicated agreement theorem, which is, I can't understand the proof, although I wrote it. But eventually we realized that in this particular case, there's a very simple proof, which is in the paper. So this is an easy example of some kind of agreement theorem, which is useful in our case.
I see. Thank you.
Yeah, and I will send the slides after some corrections. And really, if anybody here is interested in this sort of stuff, then please contact me, because I have the feeling that not so many people are interested. So know that every mathematician is interested in their own research and they're completely disinterested in anybody else's.
Unless it's epsilon close.
Exactly.
Well, I'll just keep asking inane questions, and please feel free to interrupt me, everyone else. But if we went back to this this initial, like the statement of the main theorem, so we have this mysterious f of degree d, and then we have this class of special functions g that we know things about, we know structural things about. These are kind of like the representatives from these,
Right.
thinking of like clouds of f's, and there's a g nearby. Okay, so I guess what's not clear is that there could be such a g that has no degree d f's nearby. This is a possibility.
Well, no, it's not a possibility. Well, first of all, because G is a degree D function.
Okay. Then I have to close. So every such G has an f, has one of these f's, degree D and epsilon close to Boolean nearby.
Yeah, so what the furthermore part says that this G is itself the same, it can function as an f.
Yes.
Okay, and the only thing is that this is epsilon close and here your order epsilon close. But if you don't
Yes.
care about that, then yeah.
Yes.
So it's exactly like you said. So we find these representatives out of each cloud. So these representatives maybe don't lie in the center of each cloud, but they're not too far off.
Mm-hmm. Thanks so much. This has been really interesting.
I have a question.
Yeah.
I don't understand how you define degree if your function is on the symmetric group.
Okay. Yeah, I did not do it, but I'll do it now. So yeah, you can parameterize the symmetric group using these indicators, xij. Yeah. And you can write every function as a polynomial in this xij. Okay, for example, the delta function you can express this way. So in particular, every function is a degree n-1 polynomial. So this gives you a definition of degree, and this definition agrees with the representation theoretic definition of degree. So if you look at the isotypical components, then they are parameterized by partitions. And the number of boxes beyond the first row, or the sum of all the parts but the first, this is the analog of the degree. So like your degree is the largest degree of an isotypic component on which you have any kind of non-zero mass. This is the same. It turns out to be the same degree, same parameter.
But the paper, which is now we have the address. It doesn't have anything about symmetric group. It's just the commutative case, right?
Right. So the paper for this symmetric group is called Boolean functions on Sn, which are nearly linear, and you can find it in discrete analysis. So it's also on my homepage. And also I can recommend harmonic polynomials and perfect matchings, where we give an analog of the Fourier expansion for the symmetric group, which also explains this degree in a more sophisticated sense.
Thank you.
All right. Well, thank you everyone for attending, and thank you so much, Yuval, for this talk. We will post the recording and the slides on the PAW website soon. And yeah, have a great day. See you next time.
Okay.
All right. Thanks, Yuval.
Bye.